Hello and welcome to my Lab 3 video submission titled Black Hole. So first we're going to need to know some equations before we begin. We have Newton's second law, or the momentum principle, where F net is equal to dp over dt, and the components that make up F net are the parallel and perpendicular components. Parallel component has to do with acceleration, speeding up, slowing down, whereas the perpendicular component has to deal with the direction, so curving motion. And then we have the momentum formula, where momentum is equal to mass times velocity. And then we have the velocity and position update formulas that we've been using these past couple labs. And then lastly, we have the gravitational force equation, which we'll be using a lot during this lab. And we'll be solving for different variables in this equation, not just the gravitational force. So this lab is broken up into two parts, part 1, part 2. Part 1 will be finding the mass of a black hole. We know a star's orbit around this black hole, and we'll work backwards to find the mass. And then a discussion will be held differentiating between the parallel and perpendicular components of the net force versus the rate of the change of momentum. The second part of this lab, we're going to be pretending we are spaceships on a ship trying to avoid crashing into a planet or a black hole. And in order to do this, we need to find the initial velocity. And then we're going to find the initial velocity needed to actually orbit the black hole. We want to stay in orbit. So first we have part 1, finding the mass. So a star is orbiting a black hole, and we want to find out this mass. We have some given information, the orbital coordinates, the mass of the star, and the change in time. Then we're going to input momentum, velocity, F net, in the gravitational force equation. You'll see in the code next, and this will output the net force and the mass of the black hole. So here's the code. On the right side, you can see what we started with, the seed that randomized the orbital coordinates, and then we have the mass of the star. And then on the left side, you can see where we actually put in the physics equations. We have momentum, then we have change in velocity, change in momentum, then we have the rate of change of momentum, and then we set that equal to F net, and then we find the parallel component of dp dt, and then we set that equal to F net parallel, and then we find the perpendicular component, then we set that equal to F net perpendicular. And then we solve for the mass of the black hole by rearranging the gravitational force equation. And this will produce this. There you go. You see the F net is the orange arrow, the perpendicular component is the teal, and the parallel component is the magenta. And there it goes. There's the star in its orbit around that black hole. And as you saw, the code outputted a bunch of different masses of the black holes due to several different calculation loops. And so I averaged them, and I found the mass of the black hole to be 8.78 times 10 to the 33 power kilograms. So what does this mean? Does the net force and the rate of change of momentum have the same parallel and perpendicular components? Are they different? Well, mathematically, we know that they are equal. As you saw in our code, we set them equal to each other. However, if you noticed, we would always solve for dp dt first and then set it equal to F net. And this is because these components can be solved for by observing the star's conditions, such as position, velocity. We know that the F net, or the net force, cannot be solved for. That's why we had to just simply assign it a value without the mass of the black hole. So moving on to part 2 of the lab, we're avoiding a crash. So again, we're on a ship, we're orbiting a black hole, we land on a planet. We want to know what is the initial velocity needed to get off this planet and not get caught into the black hole. So we're going to input a couple of these informations: mass, net force, velocity, and the ship speed. This is the variable we're going to be playing around with. This is going to output the planet speed and the ship's trajectory in a model. So here we have the code. On the right is the calculation loop. We use the gravitational force equation to find the net force on the planet, because both the ship and the black hole are acting upon it. And then we found the net force of the spaceship, where the planet and the black hole are acting upon it. And then finally, we added the velocity and position update formula to the planet and the ship to mimic its movement. To the left, we can see that I just played around with the speed, and I found it to be 8.6 times 10 to the 6 meters per second. And this is what it produced. It shows the planet's trajectory in teal and the ship's trajectory in magenta. As you can see, it leaves the planet almost touches the black hole, and simply leaves, exits towards space. Again, there's the speed, or the initial velocity needed. But what if I wanted to orbit this black hole? I didn't just want to leave. So I played around with the speed again, and I found it to be around 7.611 times 10 to the 6th meters per second. I knew it had to be maybe a little bit slower to allow the gravitational pull of the black hole to bring us in. Thanks for watching.